the world who are manufacturing these kind of structures in the same way. They build it with the same thin walled profiles. So the objective of my thesis is to find a different configuration to optimize these structures. So what we are working on, first of all, the safety verification, then we have the warehouse optimization, and then I compare between the general method and the EN standards for the upright verification, and finally the diagonals area reduction influence. So as we can see in this slide, we have our first model, the first case of a study, and here we can see the second one. Will be shown in details in the next slide. Here we can see the transversal section of the first model. We can see that we have 2 external shoulders and 4 external ones. The upright height is 30 meters and the section width is 30 meters. We also have 11 load levels of space, 2.6 meters each, and a pallet weight of 800 kilograms. Moving to the longitudinal section, here we can see the longitudinal section. It composes of 28 transversal cross sections, and the bay length is 3.2. We have 4 bracing towers and 11,800 pallets. Now moving to the profile used for the upright. On the left, we can see that the S profiles with different thicknesses starting from 2 until 4. And here we use also the reinforced profiles at the bottom of the columns to increase the resistance, because at the bottom we have high axial forces and bending moments. Now going to modeling. On the left we have the real structure as built, and here in the second image we have modeled the structure on south. We consider the central lines of the members, and this one is with the eccentricity, without ignoring the eccentricity between the members. For the third one is when neglecting the eccentricity between the diagonals, and the uprights when it's lower than 20 millimeters. Now moving to the general method, which is the method we use to verify the uprights. First of all, to do the resistance check, we have to satisfy the first relationship. And for the instability check, the general method, the code requires that we do a finite element analysis to obtain the data to perform this method. As we can see in this slide, we did a comparison between the safety indices for the real case and with the case with ignoring the eccentricity. As we can see, for the real case, the safety index is larger than 1 for 2 families of the member, which are the families at the base of the uprights, because we have higher axial forces and bending moments. And we also see that for the real model, the number of the unverified profiles are larger than the one with eccentricity, because because of the eccentricity, we have higher axial forces and bending moments. Now, moving to the second case of the study. Well, in this case of a study, we wanted to optimize the effective wind on our structure. So we reduced the number of the internal shoulders into 4 instead of 12. So now we have 4 external shoulders and 4 internal ones. The width of the section now is 14 instead of 30 meters. And yes. Then we move to the model 2B. Here in this model, we reduced the height of the upright from 30 to 28.7. And now we have 10 load levels instead of 11. And each one is spaced 2.7 instead of 2.6. Now moving to the optimization of the first model. So in this model, we joined each 2 shoulders into 1 large shoulder. So now we have 2 external shoulders and 6 internal ones. Then we use different types of profiles for the column. The first family were the hollow tube sections, and then the HIE and HAV, and we compared it. We'll see the comparison later between these models. Now, to describe like the way that the pallet load will be distributed after eliminating the central upright, we use the zeta beam to support at the center to support the pallet load. Okay, further optimization were done on the first model with using the K bracings. So now we have, instead of two external shoulders, we have only one external shoulder, and instead of these four external shoulders, we have one big shoulder. And we also considered two models, with the one at the above with the eccentricity between the bracings, and the one at the bottom with no eccentricity. Okay, so in this chart we can see the comparison of the weight between these models. So finally we got that the model with hollow tubes is the lightest one. So this is the optimized model, the most efficient solution, the one with the hollow tube sections. These are the results obtained for this model, the buckling analysis, the model analysis, and the maximum displacement. Now looking to the longitudinal section, I studied different bay lengths. I started with two bays, then 4 bays, 6 bays, and 8 bays, and finally 10 bays. And based on the comparison of the safety index between these models, the change in the safety index were small. So I considered the model with 10 bays to be implemented because the cost of this model will be the lowest. Now moving to the optimization of the second model, we use different types of profile called the M-series profile. These profiles are characterized by greater area with equal thicknesses, and also they have comparable inertia, so they have higher resistance. So now to the diagonals area reduction influence. So as we can see, as we reduce the area of the diagonal, we see that the safety index decreases locally. But when we go to the global behavior of our structure, we can see that as we reduce the diagonals area, the maximum displacement increases and the buckling factor decreases. So comparing the three previous models, we get that the model with the M-series profile is the lightest one. A further optimization on the second model were done. So here we studied the behavior with different pallet lengths. So we have 5 models with different pallet beam lengths. So the number of the section will be different. Yeah, this table shows the comparison of the weights between the S series profiles and the M series profiles of the total weight with different pallet beam lengths. This chart shows the comparison. We can see that for the first two models, we have that the S profiles, the weight is lower than the M series, while for the other three, we have that the M series profile is lower than the S profiles. Now moving to the comparison between the general method and the method indicated in the EN standards, we can see that for some members, the verification checks were not satisfied. And this is because for the general method, we analyzed the behavior of the member in a plane, while in the method indicated in the EL, we studied, we directly considered the flexural torsional behavior of the members. So a further optimization on the model number 2. Here we can see, first of all, we use the double shoulders with 4 pallet beams, IPE profile. The second one is the 3 pallet beams with SFB details, like the slim floor beam, where we have the lower flange of the I beam double the upper flange. And the third model is with the one with the zeta palette beam. So finally, we compared these models, and we obtained that the one with the 3 palette beams with 4, with 4, the 4 you see is the lightest one. The last modification we're done, like we considered now joining the 2 external shoulders into one large shoulder, and the 4 internal one into a big one with the K bracings. And for the central, and as you can see here, for supporting the palette, we use the Z profile and omega profile to support the inner palettes. So comparing all the other models, we obtained that the lightest one is the one with the K bracings, or you see. So final conclusions, we initially started with this structure, the 4 external shoulders and the 12 internal ones with S profile upright. So then the most efficient solution is the one with now 2 external shoulders and 6 internal ones with hollow tube sections. The difference in weight is 24%. Moving to the second model, we had 4 external shoulders and 4 internal ones with S profiles. The most efficient solution is the one with the same number of shoulders but using the M series profile, and the difference in percent is 9%. Thank you.
Thank you. So the referee for this thesis is Professor Bernuzzi.
Okay. Thank you, Yara, for your work. I really appreciate the thesis that was written very clear, the presentation. I have only a small question. You presented the results in comparative terms, making reference to the weight of the structure, that means the weight of the upright, of the rear frames, and the beams. Why not the cost? And only the weight. That is a very important parameter, but should be more interesting due to the fact that the cost of the frame is associated with the weight. Why not directly the weight?
All right, thank you. I considered only the weight parameter to distinguish between the models because the cost of the material and these structures is different from a country to a country. So here in Italy, it's different than back in my country. It's different like around the world. So we can't consider it as a parameter to compare the models.
With a more general data,
Yeah.
then depending by the country, you can.
Yeah.
Then, do you have other question?
There's a curiosity about the type of analysis that we use. Did you use structural analysis in linear elastic range?
Yeah, in linear elastic range. Yeah.
What about stability?
Oh, yeah. Study. We considered in the general method. We considered the instability check, and also we did the buckling analysis on top, so to get the buckling factor and check the instability of the structure.
Other questions? Thank you once again.
Thank you. Thank you.
Siamo all'ultima presentazione. Luca Beretta.
Poi si chiama Beretta. Ok. Beretta. Devi presentare, no?
Vedendo l'uscita non so.
Ma l'uscita è quella lì, capisci? Questa è
così.
l'entrata. Per il Covid hanno messo il profilo.
prima.